Well, the last thing that we're going to talk about in this chapter on exponential and logarithmic functions is applications or modeling these types of equations. Now, the one equation that we're going to focus on in this particular set of videos has to do with growth and decay. And there happen to be a lot of exponential and logarithmic functions out there to model all sorts of real world data. We are going to be focusing on this growth and decay model because it is really used a lot as well. You see it a lot in the sciences whenever you're talking about the decay rate of certain things. If we wanted to talk about the decay rate or how fast certain drugs come out of our bloodstream, that's another thing. And you can also use a growth model to predict, say, population or something like that. So that's kind of what we're doing in these couple of examples that we're going to work together. Here I have for you the model. It's given by A equals A naught e to the kt. If you think back to when we did compounding interest, this formula looks a lot like our PERT interest, where our PERT formula, compounding continuously, which was A was equal to P e to the RT. So all we're doing is taking a similar formula and rearranging some of the, or replacing some of the variables in it. Let me explain to you what each of these variables means in our model. A over here on the left hand side is going to be the amount at any time t. That's the amount for some time t. A naught is going to stand for the original amount. K is going to be a constant, and it is either the growth or decay rate for whatever model we happen to be looking at. And most of the time we have to solve for that constant and then put it back into the model, which is what we'll see that in a second. And then T, of course, stands for some time. So this is the model that we're going to be using, and let's look at this first example together down here. This says that, and let me leave our model up there. This says that in 2000 the population of Israel was approximately 6.04 million, and by 2050 it's projected to grow to 10 million. We want to use the exponential model in which t is the number of years after 2000 to find an exponential growth function that models the data. After we find the model, we're going to then predict what Israel's population is going to be when the population is going to reach 9 million. So the first thing we want to do is let's go in and kind of pick out some of this data so that we can come up with a model, and let's figure out what information is in here that can be replaced in our formula. So I'm looking at this, and I know that in 2000 Israel population was 6.04, and by 2050 it's projected to grow to 10 million. Our model that we're going to create starts at 2000. So since in 2000 the original amount was 6.04, that's going to be our A naught. So A naught is equal to 6.04. That's the original amount for the model that we want to build. Now, the next piece of information says that by 2050 it's projected to be 10 million. And that is what we're going to use for A. So 10 is going to be the projected amount. The next thing we want to look at here is time. We need a time. So T is related to this projected amount here, and that is going to be 50, because we are 50 years after the original amount of 2000. So this is 50, because we are 50 years after our initial start of 2000. So I have everything that I need to plug into my model, because what I'm going to do is I'm actually solving for the constant K. The constant K, which is our growth or decay rate, is specific to this question right here, or this idea right here about Israel's population. So while we are going to be using this model in all sorts of different situations, the K that we solve for is going to be specific to projecting Israel's population starting from 2000 and being given by this data. So let's go replace this stuff into our model, I have 10 is equal to 6.04 e to the 50 times k. And so I just wrote 50 in front of k. Now k again is the part that I'm actually solving for. Notice that k is up here in the exponential position, so that means that we're going to have to solve this exponential equation. We do that by first dividing both sides by 6.04. So I have 10 divided by 6.04 is equal to e to the 50k. I know, or I feel like this is going to give me some sort of decimal value, and I'm going to just try to avoid any rounding errors, so I leave this as a fraction as I work through the algebra here. Now, k again is still up here in the exponential position, but e is all by itself. So that means I have this whittled down enough to where I can now take the natural log of both sides. So the natural log of base e just gives me the exponent 50k, which is what I needed it to do, and then this is just going to be the natural log of 10 divided by 6.04. And I switched I made the natural log of this to the right hand side because I like my variables on the left, so that's how come I happen to do it that way. Now I'm still trying to solve for the variable k, so I'm going to divide both sides by 50. So I have the natural log of 10 divided by 6.04 divided by 50, and I need to know what is the decimal value for this expression right here. So we're going to put this into the calculator. So if I pull up my calculator, then I'm going to take the natural log of 10 divided by 6.04, close my parentheses so I know that I'm out of the log portion, and now I'm going to divide it by 50. And when I do that, rounding to two decimals, you see that I get 0.01. 0.01. So 0.01 is the constant that is specific to this model, to this growth model, for Israel's population. So let's write our model down here. The model is going to be A equal to the original amount, 6.04, times e to my k, which we found out to be 0.01, times any times time. All right, so there's our model right there. Now, if I want to answer the second part of this problem, it says, in which year will Israel's population be 9 million? So this is going to be the projected amount. This is the amount for any time t. So we are going to plug 9 into our formula here, or our model, 6.04 e to the 0.01 t. And now I'm going to solve for t, which is up in this exponential position. So what do? We're going to divide both sides by 6.04. So this is 9 divided by 6.04 equal to e to the 0.01 t. Again, I can now take the natural log of both sides. When I take the natural log of both sides, I get the natural log of e just gives me the exponent. So 0.01 t is equal to the natural log of 9 divided by 6.04. And now I'm going to divide both sides by 0.01. So t is equal to the natural log of 9 divided by 6.04, which is divided by 0.01. And I am going to find out what that value is using my calculator. So we'll leave it on this side over here. I think I'm going to cover it up. But what are we taking? We are taking, let me get it so we can see the whole thing. We're going to take the natural log of 9 divided by 6.04 this time, close my parentheses, divide that by 0.01, and I find out that that is, rounding up to the nearest year, that would be approximately 40. So that's approximately 40. Remember that my original starting date was 2000, so I'm going to add that 2000, I'm going to add it to it. And in other words, in the year 2040, Israel's population will be 9 million. And that's how we're going to start doing our growth, exponential growth and decay model.